Good afternoon. Thanks, Jie, for the introduction. And my name is Siyang GAO from CTU and the Department of System Engineering and Engineering Management. So before I start, I want to say that I'm really glad to make a presentation here. And I recall that the first time I met Professor Ho was back at 2013, when we were at the still conference at Automation Science Engineering, but that time was at Madison. And at the time, I asked Professor Ho, in your opinion, what do you think, how to become an excellent and a successful scholar? And I remember that he said, do good research and present it in some distinguished conferences. So here it is. I don't know if my research can be considered good in the eyes of Professor Ho and all the experts sitting here, but at least I'm glad that I have the chance to present here. And also thanks for Yao for letting me. Okay. So the title of my talk is Optimal Opportunity Cost Selection Procedure. So this is joint work with Dr. Wei Chen, which is my twin brother, and Professor Shi, who was my PhD advisor. And you'll probably find that this research is a little different from the research Professor Shi just introduced, all those manufacturing problems, because it might be because I'm lucky enough that I'm not the type of 1/3 of your PhD students who focus on the more theoretical academic problems. So I do not need to do all these kind of field trips a lot of times each year. Okay. So here's the outline of my talk. First, I'm going to give a brief introduction of simulation-based automation problems. And then next, I'm going to introduce the formulation of the ranking selection problem in this research and propose the selection procedure. Next is numerical experiments, followed by a quick summary. So simulation automation problem can be mathematically described like this. Okay, suppose we are going to minimize the objective function fx, and the x is a decision variable which belongs to a solution space theta, which can be discrete or continuous. In practice, we do not know the value of fx, but it can be expressed as the expectation of some random variable, and we can collect some samples of this random variable using our simulation model. In practice, many real-world systems, they are very complicated and might not be able to be described by a traditional mathematical model. So, and the simulation model provides a faithful way to describe them. Therefore, a problem like this can be very common in practice. And the objective function fx, we do not value of it. And what we normally do is that for each x, we generate some simulation samples, and we find the sample mean of them. And we use this sample mean as an estimate to estimate the value of fx. But we all know that this estimate converges only at a rate of 1/² n to this fx, where this n is size of the samples. So this rate is relatively slow speed. This means that if we want to have a relatively accurate estimate for this fx, we might need a large number of samples. So one major difficulty for solving simulation optimization problem is that the time to perform one simulation run for some real-world systems might be very long. Okay, so this table summarizes some real-world systems and the time to make one simulation run for them. So the first is computer network, and the time to perform one simulation run of the 1,000 second dynamics of it needs 1.5 hours. The second system is a large-scale electric power grid, and the time to perform one simulation run of the 30-second dynamics of it after a failure event is 2 hours. For transportation network, to perform one simulation of the 24-hour dynamics of it needs 2 hours. And the last for turbine blade design, and the time to perform 3D extrusion simulation with finite element methodology needs 7 days. So we know that for each simulation, we might need to generate multiple simulation runs and use a sample mean to estimate the performance of it. And to solve the simulation problems, we might need to generate estimated performance of a lot of solutions. So it becomes very important for us to make a good use of our time and the compute power during the process of simulation optimization problems. Okay, by the way, all this data were taken from the book, Ordinal Optimization, Soft Optimization for Hard Problems. It was mentioned by Professor Ho this morning, mentioned by Professor Chen just now, okay? Thank Professor Ho and Professor Zhao for this very nice book. I've learned a lot from it. Simulation optimization problems can be generally classified into two categories. The first is, we can call it a search scheme. That is, when the solution space is large and the time only allows us to evaluate a small fraction of the solution space. And the major research question here is how we are going to search the solution space so that we can reach the optimal solution or some near optimal solutions. So some methods along this line of research include a gradient-based approach, some response surface methodology-based search, and meta-heuristic algorithms. The other theme, we can call it a comparison theme. That is, for such problems, the solution space is finite, and the simulation normally allows us to evaluate all the solutions in the solution space. And the major question here is that how we are going to allocate our simulation budget, or say simulation time, to all those solutions, such that the best solution can be better selected. We know that in finite time, we cannot select the best solution with certainty. And there are different ways to measure the quality of our selected solution. And there are two common measures. One is the probability of a correct selection. The other is the expected opportunity cost. So I will use a very simple example to explain these two measures. Okay, suppose we have 100 designs for a queue. Okay, design I has a mean waiting time of I minutes. And we want to select the design with the minimal mean waiting time. And of course, design 1 is the best design because it has only 1 minute mean waiting time. So for expected opportunity cost, you see, first, for opportunity cost of a design, this is the difference in mean between this design and the best design. Okay, so for the best design, design 1, opportunity cost is just 0. And for design 2, the opportunity cost is just 2 minus 1. Okay, so 1. And of course, for design 100, opportunity cost of it is 100 minus 1, that is 99. And we let T hat to be the observed best design. Then expected opportunity cost, UC, can be defined as the expectation of the opportunity cost of the observed best design. I think this UC measure is kind of like similar to the regret measure Professor Hong just mentioned in his talk. But I think there is some difference, and this difference is also related to Professor Xia's the question asked just now. I think UC and rank selection problems, they are just focused on the final selection. So it's supposed that we have different stages in the sampling process, but we only focus on the last stage, the thing that's output from last stage. But for the measure like regret or say MAB problem, we might care about the output from each stage in the sampling process. I think that's a major difference between this UC and the regret measure. The other measure is the probability of a correct selection, PCS, and this is very simple. This is just the probability that our observed best design is the real best design. For PCS, there might be a minor issue here. So suppose we cannot select the best design. Then from PCS point of view, selection for design 2 and design 100, it will be the same because they are both incorrect selections. But from the decision maker point of view, selections for design 2 and design 100 are quite different. So design 2, although this is not the best design, the performance of it is already very close to the best design. So we are kind of okay that if we end up selecting design number 2. But we are very reluctant to select design 100 because this performance of it is far from the best design. PCS, this measure fails to reflect our preference over all these different incorrect selections. But UC incorporate our preference. We can see that the OC of design 2 is very small and the OC of design 100 is very large. So in this research, we will use UC as our measure to evaluate the quality of our select design. I hate to do this, but I will quickly introduce some notation. Okay, the N is the total number of simulation replications. It's also the simulation budget we are going to allocate to all the designs under consideration. And the K is the number of designs we are considering. And the mu I and the sigma I squared, they are the mean and the variance of the simulation samples of design I. And the Ni and the alpha I, they are the number of replications and the proportion of the total simulation budget allocated to design I. Xi bar is the sample mean of design I. And the T and the T hat, they are the real best design and the observed best design. And we have more notations. I will skip that. And we just need to keep in mind that they have been defined. And we also have assumption that the simulation output samples are independent from replication to replication and independent from across different designs. And this is also a very common assumption in the literature of ranking selection. Now the selection selection problem with UC can be formulated like this. Thanks for Professor Shi. She has shown this slide for me in her talk. Okay, so the goal is to minimize the UC, and the variables are alpha 1 to alpha k, which are the proportion of the simulation budget allocated to all the designs. And these sum up to 1, and this proportion, they are all non-negative. And the major problem for solving such a selection problem is that the objective function UC, it does not have an analytical expression. And what we propose to do is that we will find the approximation for it using an upper bound. And this is the upper bound we find in this theorem, okay? And it can be derived using the buffer inequality and the large division theory. And we call this upper bound approximated expected opportunity cost, AEOC. So the problem in the previous slide can be rewritten like this. We are going to minimize AEOC, while the variables they are the same, still the proportion of the simulation budget allocated to each design. And they still sum up to 1, and they are all non-negative. We call this problem P. And this is a problem, this is a target problem in this research. We can next show that this problem P is a convex optimization problem. So if you are familiar with Proficient's OCBA problems, OCBA formulation, you will see that this is very similar to an OCBA formulation. And for such formulations, normally, if we want to prove that such problem is a convex optimization problems, we normally need to assume that the simulation budget goes to infinity. That is, we normally need to make the symptotic assumption. But in this theorem, we do not need to do that. So we do not need to let the simulation budget go to infinity to prove this is a convex optimization problem. So this is closer to reality, and this is stronger result. Next, we can prove that we can prove two automatic conditions for this problem P in the previous slide. That is, any solution that satisfies these two conditions is the optimal solution of problem P. Also, this result is not based on the symptotic assumption. We do not need to let the simulation budget go to infinity. Also, in the literature of simulation optimization, it's normally assumed that the simulation samples are normally distributed. But this result, we do not need to assume that either. We can allow the underlying distribution to be general light-tail distribution. Okay, so next, we'll try to interpret these two automatic conditions. We will further introduce this U and the VI VI is for each non-best design. And based on these two notations and these automatic conditions C1 and C2, they can be rewritten like this. U equal to 1 and the VI equal to Vj, where I and J are two different non-best designs. Next, we have a proposition showing some derivative properties for U and VI. Now let's first look at this C1. It requires U equal to 1. Suppose we have 5 designs and design 1 is the best design. And suppose that for some allocation, U is greater than 1. Okay? Then from here, U need to be decreased. And from here, alpha t, the proportion of the simulation budget allocated to the best design, need to be increased. That is, for some allocation, if U is greater than 1, we need to allocate more simulation replications to the best design. Okay? So on the other hand, if for some location U is smaller than 1, from here, U need to be increased. And from here, the alpha I the proportion of simulation budget to non-best design need to be increased. That is, for some allocation, if the U is smaller than 1, we need to allocate more simulation replication to the set of non-best designs. That is, that if we are trying to understand C1, it's by letting U equal to 1, we are trying to keep a general balance between the simulation budget allocated to the best design and the set of non-best designs. Okay. Next, we look at this C2. It requires that the V values of all the non-best designs are equal to each other. Suppose that for some allocation they are not equal to each other, and the V value of one non-best design is larger than all the others. Okay. In this figure, we let V3 to be this design, let design 3 to be the design with the largest V value. Then from here, we know that the value of design 3 need to be decreased. And from here, we know that alpha 3, the proportion of simulation budget allocated to design 3 need to be increased. That is, for some budget allocation, if the number design, a number design, its V value is larger than all the others, we need to allocate more simulation replication to this number design. Okay. So to interpret this condition C2, it's trying to adjust the number of replications allocated to all the non-best designs. So to summarize, for C1 and C2, suppose that we have more simulation replications to be allocated to the one of the designs under consideration. C1 tells us whether we should allocate it to the best design or one of the non-best designs. And if it turns out that we should allocate it to one of the non-best designs, this C2 further tells us which non-best design we should allocate it to. Okay? So based on this interpretation, we can design an algorithm. We call this optimal EOC allocation, OEA procedure. So it basically follows the explanation I just provided. So at the beginning, we provide an equal number of allocations to all designs under consideration. And then at the beginning of each iteration, we provide a small incremental budget. And if the estimated U is greater than 1, we allocate this incremental budget to the estimated best design. Okay? Otherwise, we allocate this incremental budget to the non-best design with the largest estimated V value. And it iterates until the simulation budget is used up. To better understand this OEA algorithm, we show a typical OEA run, a typical run of this algorithm. We test it on the example with 10 designs, and here are the mean of the 10 designs, and here are the variance of the 10 designs, and the best design is design 1. So at the beginning, we provide an equal number of replications for all designs, okay, 20 replications for all of them. And here is the sample mean of them. And of course, design 1 has the best sample mean, so design 1 becomes our estimated best design. And here is the estimated U value, 8.13. And here is the estimated V value for all the estimated non-best designs. And according to the algorithm, because estimate U is greater than 1, so in the next iteration, we will provide our incremental budget to this estimated best design. Okay. Now it becomes iteration 51. And in the past 51 iterations, we have allocated our incremental budget all to our estimated best design, that is design 1. And design 1 number of replications has been increased to 71. And for the rest designs, their number of replications still remain at 20. And here is updated sample mean. And the estimated best design is still design 1. Estimated U value is 0.98. This is the first time the estimated U value falls below 1. Okay? And from our algorithm, in the next iteration, our incremental budget should be allocated to the non-best design with the largest estimated V value, which will be design 2, because this has largest estimated V value. Here is iteration 1800. Okay, so now all the designs have more or less received more replications, and the design 1 and design 2, they have received most of the simulation budget we have. And here is the updated sample mean, and the estimated best design is still design 1. Now estimated U value is very close to 1, and all the estimated V value are very close to 0.01. So they have almost achieved automatic conditions that u equal to 1 and all the vi are equal to each other. And if we stop here, we'll end up selecting design 1 because this is our observed best design. And it is indeed a correct selection because our best design is design 1. Okay, next, let's consider an issue here. So in the literature of simulation optimization, it is often assumed that the simulation samples are normally distributed. And of course, in this research, we have relaxed it to have a general distribution. But we would like to consider what's the influence of the normal assumption for the final optimal allocation. That is, if the simulation samples are not normally distributed, our normal assumptions, how is this normal assumption is going to affect our optimal allocation? Okay, so it's very difficult question. So we'll only use some numerical results to give some intuition. So we use 4 examples. 2 of them are exponential. In 2 of them, the simulation samples are exponentially distributed, and the other 2, the simulation samples are Bernoulli distributed. And for each example, we have 3 designs. For the first 2 designs, this lambda is the rate parameter of the exponential distribution. And for this last 2 examples, this Q is the success probability of the Bernoulli distribution. And for all the 4 examples, design 1 is the best design. And here is the optimal allocation. We can calculate that based on the automatic conditions we just derived. Next, we do this thing. We are going, for each example, we are still going to consider 3 designs. But the new 3 designs have the same mean and variance of the original 3 designs. The only difference is that now the simulation samples follow normal distribution. Okay, I'll be quick, sorry. Now to follow normal distribution. And we'll calculate the optimal allocation again and see how far it is from this original optimal allocation. Okay, if it's far away, it means that the normal assumption has a great influence on the final optimal allocation. Otherwise, if the 2 allocations are very close to each other, it means that the normal assumption does not make a very great influence. Okay. And here's the result. Okay, we can see that for the 3rd example, the 2 allocations are close to each other. Okay, for the first 2 examples, the difference are bigger, and for the last example, the difference are the biggest. So one possible factor that might be able to explain this result is the skewness of the underlying distribution. So we all know that the normal distribution is symmetric, so it has the skewness of it is 0. Okay, so for the 3rd example, all the 3 Bernoulli designs, they have their skewness are very close to 1. So the skewness of the 2 cases are close to each other. So is the difference in the optimal allocation of these 2 cases. Okay, so for the first 2 examples, we know that exponential distribution has a constant skewness of 2. So the difference is bigger in skewness. And so is the difference in the optimal allocation. In the last example, the 3 Bernoulli designs, they are highly skewed. Their skewness are far from 0. Okay, so the 2 optimal allocations, they are also far away from each other. So that is, so if the simulation samples are not normally distributed, and if they are kind of like symmetric or has a very small skewness, we might be able to assume that they are normally distributed because it might not affect the final optimal allocation a lot. But if the underlying distribution, they are highly skewed, we might want to be careful when we make the assumption that the simulation samples are normally distributed. And this observation is the same as a paper here, which consider ranking selection with PCS measure. We next quickly consider another issue. That is, in the numerical examples, we always observe that the algorithms designed for EOC, algorithms designed for PCS, they have very close performance. And this is a result taken from this paper. We can see that no matter we use PCS measure and no matter we use EOC measure, we have four curves tangled together. 2 of them are designed for EOC and 2 of them designed for PCS. They have very close performance. Same for the EOC measure. They have very close performance. Another example is the same. These 4 curves have very close performance. 2 of them EOC, 2 of them PCS. Same here. So this is, it should be surprising because EOC and PCS are 2 different objective functions. But it turns out that the performance, the algorithm designed for EOC and PCS usually have a very close performance. So this phenomenon actually can be explained in theory. So we can prove that the budget allocation that optimize EOC and PCS as the simulation budget goes to infinity will be the same. So it's not hard to it's become not hard to imagine that when the simulation budget is large enough, the budget allocation that optimizes EOC and PCS will become very similar. So specifically, we have the EOC-based selection problem like this. We have a PCS-based selection problem like this. Okay, we can let the simulation budget go to infinity and consider a symptomatic version of the EOC-based selection problem like this. Maximize PCS probability of correct selection is the same as minimize the probability of false selection. Okay, we further consider the symptomatic version of minimize PFS. And it can be proved that these two problems are the same. So essentially, no matter we want to optimize EOC or PCS, when the simulation budget N is large enough, we are both trying to minimize the probability of incorrectly compare the best design and the non-bad design that is the most difficult to correctly observe. Okay, so come again. It's a little tricky here. So no matter we want to optimize EOC or PCS, as the simulation budget is large enough, we are both trying to minimize the probability of incorrectly compare the best design and the non-bad design that is the most difficult to correctly observe. Okay, so that's partially that's kind of explain this phenomenon in numerical results, because as the simulation budget is large enough, no matter we want to optimize EOC or PCS, we will basically optimize the same term. Okay, so their performance become very similar. Time is limited. I'll quickly describe this numerical experiment. We have an eco-allocation for comparison, and we have two other algorithms designed for EOC, and they are designed for normally distributed simulation samples. And we use a simple SS inventory system for comparison, and we can see that our proposed OEA algorithm has the best performance. OCBL and LL, these two algorithms designed for EOC, they perform next, and the last is eco-allocation. Okay, so I will quickly summarize. So in this algorithm, we propose in this research we propose a new algorithm called OEA. Okay, so in each iteration, it provides a small incremental budget and allocated to either the best design or one of the non-bad design based on our automatic conditions derived. And this algorithm is developed based on the finite simulation budget and the general underlying distributions. So it might be well suited for real-world systems. Okay, so that's all of my talk. Thanks.
Okay, thanks, Siyang. So just one quick question. Okay.
Yes.
I know you showed that for the exponential distribution, the optimal allocation could be very different from normal. But that's in terms of the allocation proportion, right? But in terms of the actual results, say EOC, will that make a big difference?
You mean actual results is it's like results like this? So for exponential, it's our experience that we should be able to estimate the initial stage that we are going to allocate a certain number of replications for each design. If we are able to allocate all this exponential distribution example mean at the first stage very accurately, then the performance will be very similar. But for exponential distribution, it normally it's hard to give a very accurate estimate. But in this stage, the difference will be larger.
Okay.
Can I ask just one quick observation about all the
Sure,
presentation this afternoon? You know, a very real, useful, real-life metaphor I find useful in thinking about all these problems for the OCBA, ordinal transformation, and OEA, and so forth. It's a very real-life problem every one of us face. That is finding a good life partner, whether it's husband or wife. We have limited time, limited budget, and tremendous selection possibilities. And really, lots of these insights we get from these papers can be interpreted in terms of this example. that every one of us faces. And so it's useful to think that way.
Okay, thanks.
Can I echo to that? But when you choose your spouse, you only choose the one, right?
Yes. Well, in any optimization problem, eventually you only choose one. You choose the best
But
observed
also the
one, best
probability
one,
for correct
everything.
selection.
You only choose one optimization always.
You can try a lot, but just choose one.
Well, sample. Trying is sampling.
Yeah.
You're sampling. And the sample result is not perfect. It's stochastic. Some are very obvious, you can tell right or wrong, but some are not. I mean, just take the example on the transformation. What you said, you should date people with very different backgrounds in order to provide better correlation. If you only date one type of person, and you may miss some really good fit elsewhere. So it's useful to think
So maybe
about.
from results, we know that we should spend most of the time on maybe the best two alternatives for consideration.
Okay.
thanks.
Thanks for the discussion. And